All right, let's talk about the secret language that's running our digital world. Seriously, it's this hidden mathematical code that protects our data every single day. It's called a cyclic code. And honestly, it's like an invisible shield that makes everything from your music to space exploration possible. So let's dive right in.
So, have you ever really wondered how this stuff works? You find an old CD, it's all scratched up, but somehow it still plays perfectly. Or think about this, a message from a spacecraft, millions and millions of miles away, comes back to us perfectly clear. How in the world does that happen? Well, believe it or not, the answer to both is the exact same incredible piece of technology.
Yeah, the problem we're fighting against is something called digital noise. Honestly, the best way to think about it is just static, but for data. It's any unwanted hiccup that messes with the ones and zeros that make up, well, everything digital. It could be a physical scratch, it could be weird radiation from space, anything that scrambles the signal.
So first up, let's really dig into what happens when good data goes bad.
Digital noise isn't just one single thing. It can be a scratch on a DVD, it could be radio waves messing with a Wi-Fi signal, or even a tiny little hardware glitch in your phone. The point is, it's anything that can flip a 1 to a 0 or a 0 to a 1. And when that happens, your perfect data can instantly turn into complete garbage.
Okay, so how on earth do we fight back against this constant threat? Well, you fight fire with fire. And in this case, you fight bad math with better math. And that brings us to the elegant solution, the hero of this story. And here it is, the cyclic code. Now the magic word here is cyclic, which hints at its core idea, this beautiful repeating pattern. Get this, if you have a chunk of data that's a valid code word, and you just shift all the bits one spot to the left or right, that new arrangement is also a valid code word. It's this super predictable, almost musical structure that makes spotting and fixing errors not just possible, but incredibly efficient. And I'm not the only one who thinks so. People who work with this stuff all day long describe these codes as being renowned for their mathematical elegance and efficiency. I mean, that's what you want, right? A perfect mix of a beautiful idea and something that just flat out works in the real world. So, what's the secret sauce here? How does this all actually work? Well, it all comes down to a powerful little tool called a generator polynomial. Okay, I know that sounds super complicated, but stick with me. The idea behind it is actually way more intuitive than it sounds. Seriously, the best way to picture it is like a master recipe. Or maybe a secret key. Instead of writing down a giant phone book of every single possible valid code, you just have this one simple formula. That's it. This one polynomial defines the entire structure. All the rules, the whole pattern, it's all baked right into that one key. And because it's so elegant, the whole process is incredibly efficient. Here's how it works. First, that generator polynomial wraps your data in a kind of mathematical armor. Then, your newly protected message gets sent. And on the other side, the decoding system uses that same recipe to check the message, instantly spot any errors that the noise created, and poof, it fixes them.
Now, what's really cool is that cyclic code isn't just one thing. It's more like the head of a big, powerful family of codes. And just like in any family, each member has its own unique specialty. And you've probably heard of some of these family members, even if you didn't realize it. I'm talking about things like BCH codes, Reed-Solomon codes, Hamming codes. These are the absolute heavyweights of error correction. They're in your computer's memory and QR codes pretty much everywhere. And the one thing they all have in common? They all share that same cyclic code DNA.
Having this whole family to choose from is just so useful. For example, some codes are really good at fixing just one or two little bit flips, those small isolated errors. But others? They're designed to fix massive chunks of damage all at once. We call those burst errors. And that's exactly what a big scratch on a CD is. So engineers can look at the problem and just pick the perfect tool from the family for that specific job.
Okay, so let's bring this all back to the real world. Where is all this elegant math hiding in plain sight, working silently in your life right now? Remember those questions from the beginning? Well, here's the payoff. That scratched CD? It's protected by Reed-Solomon codes, which are a type of cyclic code. Those crystal clear messages from deep space? You guessed it, same thing. But it doesn't stop there. This tech is crucial for resilient data storage, and it's even being used to create new defenses against cyber attacks. I'm telling you, this stuff is everywhere.
I mean, just look at this. This is the magic right here. On one side, you have a message that's just a jumbled, corrupted mess, totally unreadable. But
Because it was encoded using a cyclic code, the receiver can use that built-in mathematical pattern to find every single error and perfectly rebuild the original. It's not actually magic, but man, it sure feels like it.
And get this, they aren't just good at what they do. In many cases, they are literally the best possible. A lot of these cyclic codes are what we call optimal. That means it is mathematically impossible to design a code of the same size that can fix errors more efficiently. You literally can't do any better. That's how powerful this is.
So really, what's the main takeaway here? The crucial point is that this elegant, powerful math is a silent force working all around us all the time. It's the invisible guardian ensuring that our incredibly complex digital world actually runs reliably.
And that leaves us with one final big question. Cyclic codes were an absolutely brilliant solution for the data challenges of their day. But now, as our data becomes more complex, more vital than ever, you have to wonder, what new elegant mathematics are we going to need to invent to protect it all in the future?